next speaker is Winsberg from the University of South Florida, and he's going to give a talk on missing the forest for the future.
All right. Well, I'd just like to thank the organizers for inviting me. It's quite a pleasure and an honor to be talking about climate science with such a terrific group of people, so many different areas of expertise here. Also, I want to just note that this work is collaborative work that I've been doing with my colleague, William Goodwin, in the philosophy department at South Florida. OK, so what I wanted to do today was take an opportunity to talk about a few papers that have come out recently in the philosophy of science literature. They have a variety of authors, but I think all three of these papers have among their authors two of our speakers at the conference today, Lenny and Rotman. And in these papers, they've been kind of articulating what I take to be a fairly powerful skeptical argument about the possibility of nonlinear models producing what they call decision-relevant predictions. So I just kind of wanted to pull apart some of the arguments that they've been giving, try to figure out what exactly the claims are and how strong the arguments are for the different claims that they make. So as I say, it's a general epistemological argument that's designed to kind of cast doubt on the capacity of a broad range of mathematical models to generate decision-relevant probabilities. And it's an argument by analogy, right? So the argument goes like this. They demonstrate that a sort of particular imperfect mathematical model fails to deliver certain kinds of reliable predictions. They diagnose that failure as having a certain kind of root. And then they argue that a broad, and this is sort of important, right? I think a broad but kind of indeterminate range of additional imperfect modeling projects suffer from the same kinds of, in a way, kind of catastrophic failures is maybe the way I would characterize it. OK, so why do I say indeterminate range of other models? Because in the various papers, I think there are different kinds of, one can tease out different lines of articulation about what the scope of the argument is. So sometimes I think the argument is alleged to have a fairly broad scope. It claims that sort of all nonlinear models are, quote, maladapted to what they call, again, decision-relevant quantitative predictions. But then sometimes the claim is a little more narrow. And the claim seems to be that we need to use caution in interpreting things like high-resolution predictions out to the end of the century. So I want to kind of, first of all, trace out and contrast the two kinds of claims that are made in the paper. In fact, I think there's going to be kind of three kinds of claims that are made in the papers. And consider for each of these three different kinds of claims what their implications would be for climate science. Then I want to kind of lay out what the base case is, what the analogy is, and what the structure of the argument by analogy is that they offer. Then I'm going to sort of draw out what I take to be some epistemologically significant distinctions, and then assess the implications of those distinctions for their arguments. So that's kind of roughly the plan of the talk. OK, so what are what I would call the wide scope claims of the paper? That the combination of nonlinear models with what they call structural model error is, quote, a poison pill that, quote, pulls the rug from underneath many modeling endeavors, that probabilities for future events to occur or probabilistic forecasts drawn from nonlinear models can't be trusted, and that not all models, while they concede, right, that not all models underlying these forecasts are useless, because while they're maladaptive for quantitative prediction, all they're sort of willing to concede, it seems like, is that they're an informative aid to understanding phenomena and processes, right? So while they may offer some qualitative understanding, all these nonlinear models, this is sort of the broad scope claim, all these nonlinear models are maladaptive to quantitative prediction of any kind. OK, so in other words, right, nonlinear models about which we have reason to believe that there's even the smallest amount, right, of structural error can be qualitatively informative, even though, right, and this is, right, one little caveat, absent a proof of stability, right, and the burden of proof is on anybody who wants to make decision-relevant quantitative forecasts. The burden on proof is on them to offer a proof of stability Absent that, they're not at all quantitatively trustworthy. So that some of the language of the paper, I think, can very easily be read to be making claims of that strength. So one thing that we might ask then is, what would be the implications of claims like that for climate science? And while the authors sort of at one point assure us that, and so I haven't mentioned this hawkmoth effect yet, but that's kind of the base case that the analogy is drawn from. The hawkmoth effect poses a serious challenge for any rational applications of, say, things like the methods of the UK SIP, I think I'll talk about in a minute. This fact casts no doubt on the reality or risks of anthropogenic climate change, for which there's evidence from both basic physical science and observations, right? Even though the limitations on prediction that they're drawing attention to, quote unquote, are debilitating for mathematical precision and just not for valuable qualitative insight. Okay? So the claim is, even though their argument in the broadest scope of that claim is meant to cast doubt on all quantitative predictions one can draw from a very broad class of models, we're meant to be assured that this casts no doubt on the reality or risks of anthropogenic climate change. But I think there might be reasons to worry about that, right? So if we look at, for example, the most recent IPCC report, and we look at their language on the importance of models for what you might broadly think of as attribution claims, right? Claims about what the source, what the causal origin of, say, observed warming of the last 50, 70, 100 years, whatever, whether one can attribute that to human causes, right? They say things like this, right? That detecting a change in the climate based on observations requires determining that the likelihood of occurrence by chance due to internal variability alone is very small, right? And this, in turn, requires an estimate of the internal variability, generally derived from, quote, a physically based model, right? And furthermore, that going on to attribute the detected change to a specific cause, for example, human activity, typically involves showing that the observations are, quote, consistent with results from a process-based model that includes the causal factor in question, and inconsistent with an alternate, otherwise identical model that excludes this factor, right? Indeed, I think the authors of the IPCC report are quite clear that attribution, attribution in the sense of finding the cause of the observed warming is impossible without a model, right? And this is, I think, for a reason that philosophers of science are pretty familiar with, right? Attribution is a causal question. Causal questions are modal questions. They're questions about what would have happened in the absence of some causal influence, right? I think a lot of commentary that one finds from climate scientists agree that there simply is no basic physical science capable of answering modal questions about the climate, because even though one can sort of write down simple equilibrium models that are based on physical science, basic physical science, there are just too many competing factors, too many potential both negative and positive feedbacks, right, to be able to reliably tell what kinds of answers one would give to modal questions like, what would we have observed had there only been stellar flares or volcanoes or various kinds of forcings, right? Okay. So again, quoting from the IPCC, we cannot observe a world in which either anthropogenic or natural forces are absent, so some kind of model is needed to set up and evaluate quantitative hypotheses to provide estimates of how we can expect such a world to behave and to respond to anthropogenic and natural forcings. So I take it that if the scope of the argument is as broad as some of the language of the paper suggests, both as broad and, as I'll argue in a moment, as kind of broad and as nuclear in its power, right, then I think it would be slightly disingenuous to suggest that this casts no doubt on attribution claims. I think there's surely some evidence for anthropogenesis just from basic science, but surely the consensus view anyway is that there's additional evidence for anthropogenesis from modeling, from nonlinear modeling. And if you think that there's an argument that pulls the rug out from under that nonlinear modeling, then surely I think you're casting it's fair to say you're casting some doubt on attribution claims. Okay. Good. So what are some other possible readings of the papers? with respect to this question of scope. Sometimes the argument is given a slightly narrower scope, right? And the argument then is claimed to cast doubt only on probabilistic forecasts that are, and here I'm going to also offer sort of two alternative formulations of the narrow scope version of the claim, that they cast doubt only on probabilistic forecasts that are sort of overly precise and local. That's a phrase that gets used a number of times in the papers. And then the sort of more obvious way of characterizing the narrow scope claim is by looking carefully at the method used in the core case that the analogy is drawn from. And then so maybe the scope should be narrowed by looking at only those probabilistic forecasts that are generated from the underlying mathematical model via the particular method that's used in the core case. But then, of course, it becomes an interesting question whether, if we're looking for a narrow scope interpretation of the kind of skeptical claims being offered, whether or not those two ways of narrowing the scope, whether they line up or not. In other words, if I narrow the scope of the claims by restricting it to overly precise and local forecasts, does that line up with the way the set of the domain of the argument if I narrow it by looking at the particular mathematical method used? Okay, so I want to talk a little bit now about ways that they characterize precision and locality, and then I'll talk a little bit about the method itself. So precision and locality, the way they characterize precision and locality, is usually with reference to this kind of this one sort of climate study that they draw a lot of attention to, the United Kingdom Climate Projections Project of 2009, what I'll refer to as UK CIP for the rest of the talk, right? And so they tell us things like, well, the UK CIP makes so-called high-resolution forecasts of 21st century climate. It does things like forecast for us the hottest day in August in a particular year. It does things like tell us what the temperature of the hottest day in central London will be in the 2080s, right? And at a certain point in at least one of the papers, we're told it's these facts, right? It's the fact that there are climate studies out there making these overly precise and local forecasts that shows that their arguments are significant, that they're quote unquote not just a hobby horse for philosophers, right? So sometimes it's reference to the existence of the UK CIP that's cited as evidence that their arguments are applicable to climate science. And that then suggests, well, maybe the scope wasn't quite as broad as it was meant to be before, because of course, why then say it's this particular study that shows we're not just spinning our wheels, that shows that what we're doing is important. Okay, so that's one way of, I think then that language suggests that the scope of the argument is meant to be restricted to overly precise and local forecasts, where the UK CIP is meant to be taken as some canonical example of an overly precise and local forecast. Good. Okay. Interestingly, and this is just, I think this is right, somebody can correct me if it's wrong, the UK CIP is not cited at all by Working Group 1 of the AR5. I think that's right. I didn't see it. I couldn't find it in there anyway. Okay, good. Let's talk a little bit about what the argument is. And the argument, again, the argument proceeds by looking at a core case and then claiming that there's an analogy from that core case. So again, it involves looking at a particular model, what they call the hawkmoth model. Basically, it's the logistic equation, right? And then it's a particular method of generating probabilistic predictions out of that model, right? And then, right, it depends on, again, an analogy and saying that other modeling projects will have some of the same failures that this modeling project has. So, good. So what's the hawkmoth effect? The hawkmoth effect is meant to be a kind of name to rival the butterfly effect, I take it, right? And it's a kind of analogous, it's an analogous phenomenon, right? Remember, the butterfly effect tells us that in certain sorts of chaotic models, no matter how close you might be to the correct initial conditions, if you wait long enough, sort of any predictability that might be associated with being close enough goes away, right? It's a kind of game of you tell me how close you want to be and how far out you want to be, and I'll tell you, you tell me how close you are and and how close you want to be in your prediction, I'll tell you how far out you have to go before your predictions become useless. Right? And this is a similar kind of claim, right? But now instead of there being uncertainty about what the initial conditions are, there's uncertainty about what exactly the nature of the model is. Okay? So there's this idea that there's a metric of distance between models, and even if I know the exact initial condition, so if you imagine that little x as being some precise initial condition, and model 1 and model 2 being two models that are as close as you like on that metric, right? As close as you like on that metric, you can kind of pull them as far apart as you like. And interestingly, what that tells you is that then if you have an ensemble, which is that little blue circle over there, if you have an ensemble of possible initial conditions, and you have these two models that are sort of arbitrarily close on this metric, right? The two models will pull that ensemble into as widely separated two blobs as you like, given enough time. Good. So that's the effect. That's the hawkmoth effect. What's the method that the hawkmoth effect? What's the canonical method that the hawkmoth effect wreaks havoc on? It's what they sometimes call the default method. This is a phrase that is used in the papers. And it's this, right? The idea is you've got some initial conditions. So you put some probability density function over some possible range of initial conditions. And then you evolve that probability density function forward in time using the dynamics of the model, right? And what the hawkmoth effect shows is, right, if you do this, right, and here you're meant to sort of imagine that over here in A, you've got two very close, you have one probability density function in A, and then you have two models that are only slightly tinily different. And after a certain amount of time, by the time you get to box D, right, the probability density functions have completely been pulled apart by two very arbitrarily close models. Okay? So it's pretty clear that in the case that they're talking about, in the case of the logist equation, and in the case of using this method, right, and this is the way to think about their argument. I think the right way to think about it is this. You've got the butterfly effect. The butterfly effect tells you small errors in initial conditions are catastrophic. You try to solve that problem by moving to a probability density function over initial conditions. But the hawkmoth effect tells you that even if you do that, even if you make that move, small errors in your model are going to be equally catastrophic to the butterfly effect. Okay? So good. So the hawkmoth effect, they then claim, plagues all models that are not structurally stable. That is, that fail to have this dynamical feature. Right? There are plausible reasons, they think, to believe that the sorts of mathematical models that scientists are typically interested in, that is to say that a very broad class of nonlinear models are not structurally stable. And therefore, it's the burden of proof is on any scientist who wants to use a nonlinear model for making decision-relevant forecasts to prove, right, that their model is structurally stable. That is, that it doesn't display the hawkmoth effect. So now I want to make one, I think, really important point here, at least as I understand the nature of this argument, right? And that is that while one could quibble about the scope of this argument, that is to say, what are the range of applications on which the argument is meant to apply, what seems pretty clear is that when it's meant to apply, it's got sort of nuclear power, right? It presents catastrophic, it has catastrophic implications on whatever predictive projects it's meant to apply to, right? It's meant to be it's meant to sort of suggest that, or at least the way I read all the papers, right, is that the cautionary tale is you will end up in these predictive tasks, to which are the ones that our argument applies to, doing the kind of thing that somebody who wants to, predict the weather way far out will be not knowing whether there's a butterfly flapping its wings over there. You will be subject to catastrophic problems. Okay? So I think that's important to keep in mind. The scope is unclear. The power is not. The power is meant to be catastrophic. Good. Okay, so one question then is, how common is this default strategy, right? Because one suggestion might be, well, the scope of the argument is that it's meant to apply to modeling projects in which the default strategy is used. So one question is, well, does the UK SIP use it, right? Not according to the authors of the very papers I'm talking about, right? So this is their own language, right? The The UK SIP probabilities are formed in a more complicated manner, combining output from multiple imperfect models using Bayesian methods. And then the authors say, well, that won't make the problem go away. OK, it's a kind of a funny dialectic then there, right? Because it seems like what you ought to show is that the problem is there, and then ask whether solutions to the problem make the problem go away. But if the argument that the problem was there depended on an analogy of looking at a particular use of a method in a particular modeling context, that's a kind of dialectically strange claim. So one thing you might wonder is, well, why think that the argument goes across that argumentative gap then? Okay, it's one question you might ask. More relevantly, I think, and this gets back to the question about scope and about sort of basic attribution claims that I think are pretty fundamentally interested in. Will using those same kinds of methods that, say, the UK SIP people use, using these more sophisticated Bayesian methods that they refer to, will they make the problem go away in more fundamental attribution cases, right? Or not? And if not, why not, right? So what is it then, if those methods won't make them go away in the UK SIP case, why will they make them go away in the other case, or don't they, right? And then we're back to maybe having to entertain the very broad scope claim, okay? And why don't they make them go away ever in any applications of nonlinear models, which of course we use for things like predicting the safety of the nuclear stockpile, predicting whether airplane wings are going to work properly, predicting whether oil fields are going to collapse when we drill them in various ways. So we use nonlinear models for all kinds of decision-relevant predictive tasks. And it's sort of an interesting question then, I think, to say, OK, if there's a kind of, if we're kind of then looking at an argument where it's unclear why the problem doesn't go away in the UK SIP case, why would it not? What's the sort of principal reason to think it'll go away in some cases and not others? So that's a question I'm sort of unclear on. Good. Deeper question, right? Does the IPCC use this, quote, default strategy? There's a pretty telling chapter that answers this question, right? There's a chapter called Near-Term Climate Change Projections and Predictability. The point of that chapter is to assess a very sort of particular and peculiar kind of climate modeling project, namely those that are used to make observation-based initial conditions. Those are, right, in that chapter, that the particular thing that's done in that chapter is specifically drawn in contrast to climate projections, right, the sort of normal IPCC stuff, which are, and now I'm quoting again, climate change experiments with models that do not depend on initial conditions, but on the history and projection of climate forcings. Simulations run in a climate projection are, quote, not intended to be forecasts of the observed evolution of the system, but to be possible evolutions that are consistent with the external forcings. So much of what we learn from the work that's actually cited by the IPCC doesn't use anything like putting a PDF over initial conditions and running it through. It does things like trying to figure out what maybe sort of generic initial conditions might be like, and then doing what look much more like experiments on possible climate models to determine what kinds of forcing relations are out there. So in a way, it's quite disanalogous in certain ways to what we see in what I'm going to call the core case that the analogy is based on. And so one has to then wonder, right, if the argument extends into, let's say, from the core case to the UK SIP, does it also extend to attribution studies? Why or why not? How far does it go? What are going to be the sort of principal bases for scoping that out, right? Right, and then we're even told, right, even of the IPCC's climate predictions as opposed to the climate projections, even those, right, do not provide forecasts of the detailed day-to-day evolution of the future weather. Instead, they provide probabilities of long-term changes to the statistics of future climatic variables. Charlotte Rundle has written a nice paper recently defining what it is to be a climate variable, right? And in a sense, right, it's part and parcel of the definition of being a climate variable as opposed to a weather variable, that it's not about point-wise, day-to-day fluctuations of some value, that it's something more diachronic than that. I'll talk about that idea in a sec. Okay, good. So I want to then ask 3 questions related to these 3 possible interpretations of their argument, right? What's the strength of the argument of their analogy to the Legis equation for casting doubt on, first of all, the capacity of a broad range of mathematical models to generate decision-relevant predictions when those modeling efforts use the default strategy? So how powerful is the argument when the default strategy is used? How powerful is the argument when a modeling project is making precise and local predictions, where precise and local is kind of defined via a canonical case, namely the UK SIP? And third of all, what's the strength of the analogy for establishing the broad and provocative claims that, this is a poison pill that pulls the rug out of all nonlinear modeling forecasts? Good. I want to then now just make a few distinctions that are going to be, I think, important to answering this question. So the first distinction is between what I would call synchronic and diachronic predictions. Okay? So I was a little reluctant to call this weather versus climate, but in talking to Lenny about this stuff yesterday, maybe that's just the best way to think of it, right? Diachronic predictions are things like the
I would be hesitant. Not too much weather-climate distinction.
Sorry?
I would be a little hesitant about drawing too much.
Okay, good, fair enough. So let's forget that. So, so by diachronic, I mean things like the average value of a variable, the maximum or minimum value that a variable takes over some period of time, the shape of an attractor of a system, things like the existence of different kinds of connections between attractors, topological features of the attractor, its dimension maybe, something like that, right? In particular, right, diachronic predictions, they're not indexed to a particular time after some seeding of the model, right? So if I put some initial conditions in at time 0, and I'm interested in what the system is going to be like at time t1, that's a synchronic prediction. If it's anything different than that, if I'm interested in the maximum value over some period of time, anything more global, anything more, that's what I would call a diachronic prediction. Now, interestingly, right, this is a very important point, I think. Diachronic predictions can be precise and local, right? The exact maximum temperature of London, Ontario over the next 100 years is a very precise and local diachronic prediction, okay? So I think one oughtn't confuse the synchronic with the precise and local. They're not exactly, I think most synchronic predictions tend to be precise and local, but not all synchronic and local predictions are synchronic. Good, okay. Another distinction, which we've talked about a little bit already, the distinction between sensitive dependence on initial conditions and sensitive dependence on model structure, right? This is this distinction between the butterfly effect and the hawkmoth effect. It's the distinction between a kind of explosive, catastrophic uncertainty that can result from your ignorance of the precise initial condition versus a kind of catastrophic and sort of nuclear kind of problem that can arise from your ignorance of the precise model structure. Okay? Good. Now this is a sort of slightly technical part of the paper that's maybe slightly over my head technically, but I think it's worth kind of looking at a little bit. This is some stuff that Connor Mayo Wilson has been working on, partly in response to Roman and Lenny's work. And he's been trying to kind of give a more precise definition of what these guys are talking about when they talk about the hawkmoth effect, right? So good. So this is a standard sort of definition of what it is for a model to be chaotic, right? And what it tells you is that if you have any two open sets, U and V in the state space, right, anywhere you want to go, right, give me enough time, and there'll be two initial states arbitrarily close together that will, after enough time, take me to these two open sets, however far apart they are later. And that's a kind of standard way of thinking about what ordinary chaos is. Structural chaos, right, is meant to capture the same kind of thing. Structural chaos is meant to capture the same kind of thing. But now instead of a space of states, you have to think about a space of dynamics, right, with a metric on it so that you know what it means, for one dynamical law of evolution to be very close to another dynamical law of evolution. And Connor defines this in terms of the in terms of the distance between the two time evolution functions being what its maximum value is, right? So if you can minimize that maximum value, then you have two dynamics that are very close. And good. So he comes up with some nice definitions of what it is to be structurally chaotic, which I think captures nicely. You can respond to that if you, later, whether you think that captures what you think is the hawkmoth effect reasonably well. But interestingly, right? Interestingly, this is about the dynamics diverging by some arbitrary amount after n steps in a discrete time evolution dynamics, right? So it's about where this system will be after n steps compared to where this system will be after n steps. It's about the applicability, I think, of synchronic predictions in exactly that way. Okay, right? So this is sort of an intuitive capture of that definition, right? Intuitively, that even for precise initial conditions, no matter where you want to go in the state space, there's some time evolution function that's arbitrarily near to the one you started with that will take you there from that precise initial condition in the same number of time steps. Good. Okay. Then there's some confusions then that Connor Mayer-Wilson raises about, well, why does it seem to be a defensible mathematical result that ordinary chaos always seems to be, or almost always seems to be, accompanied by structural chaos? That is, whenever you have the hawkmoth effect, whenever you have the butterfly effect, you do seem to get the hawkmoth effect. And yet, right, it seems to also be the case that on some definitions of structural stability that are meant to intuitively capture the same idea, right? This was, in fact, some of the things that Poincaré and people interested in celestial mechanics were very eager to prove, was that some chaotic systems were structurally stable in the sense that perturbation methods could be used to study them. Okay? So how could it be that a system that is both structurally chaotic could also be structurally stable on a definition that has the very same sort of intuitive character? And as I understand it, and I'm very happy to be corrected on this because this is outside of my pay grade, right? It has to do with what you count as a possible nearby trajectory. So if you're interested in arbitrary dynamical laws of evolution, then the nearby ones might take you quite far away. If you're interested in things like continuous and maybe 2 or 3 times differentiable functions, then the answer might be different. That's about the extent of my understanding of it. But in a phrase that I think this is what you were getting at is it depends on what your universality class of possible laws of evolution is, right? Depends on what you're considering as the set of possible laws of evolution. Okay, good. So that's something worth mentioning. About 5 minutes, good. Okay, so question 1, what's the strength of the analogy for casting doubt on the default strategy? And the answer there is, I think that question is just hard to answer, right, without really understanding carefully what the relevant class of functions is, what the relevant metric of distance is. The question just seems to me, from what I've read, the jury might still be out on that question. Okay, but I think luckily, climate science never, either rarely or never, uses the default strategy anyway. Good. Question two. What's the strength of the analogy for casting doubt on precise and local predictions? And here I think we need to, again, be careful not to equivocate between between the synchronic and the precise and local, right? I think if we look carefully at Connor Mayer-Wilson's definition of structural chaos, which I think is a pretty apt characterization of what the hawkmoth effect is supposed to be, it's about where the system will be after n steps. So it's not clear to me that the analogy is good, right? That argument by analogy has any force on diachronic predictions. But in particular, right? If it does, if the argument works on diachronic predictions at all, it's not at all clear to me why it should be restricted to the precise and local ones. Again, because whatever the scope of the argument is, it has nuclear force, right? And so it doesn't seem obvious to me why, if the argument is extendable to diachronic predictions, it's not catastrophically extendable to diachronic predictions, and why the UK SIP should be at all worthy of being singled out for criticism on this basis. Good. Now, what about the UKSIP in particular? Am I trying to argue that the UKSIP is great and wonderful and we should trust all its predictions? No. I think the intuition is probably right that overly precise and local predictions are a bad thing, right? But why, right? The slide's too big for my having 5 minutes left, but the short version of it is, I think if we want to answer the question, why are overly precise and local predictions bad, we ought to be looking at the details of the science. We ought to be looking at what features are well represented in our models, what features aren't well represented in our models, right? We should be looking at actual aspects that we understand about things, the kinds of things exactly that Linda Mearns was talking about in her last talk, right? Let's look at regional models. Let's see what they get right. Let's see what they don't get right, right? And the reason that should be the right answer, the important reason that should be the right answer for why overly precise and local predictions are bad is that, right, it's going to be important to not then throw the baby out with the bathwater, right? And it seems to me the hawkmoth argument is just too nuclear of an argument, right? I don't see how to apply it. I don't see how to apply it to cases like the UKSIP without it obliterating almost, all of applied science of the 21st century. And that just seems like something we would want to be careful not to do. Okay, good. It's not clear how their criticisms, in other words, of the UKSIP are sufficiently precise to indict the UKSIP without imputing. Here I put all of climate science, but I could have put more than that, right? Finally, good. What is the strength of the argument by analogy for establishing the more broad and provocative claims? Here I just don't know, right? This I think is a question. This is a question for applied mathematicians to give us the answer to, right? I think it would involve having to get clear on what the relevant metric of distance between the relevant distance metric between laws of evolution was. It would involve having to get clear on what the right analog of the hawkmoth effect was, because the hawkmoth effect is a distinctly synchronically characterized effect. You'd have to characterize the effect diachronically, and you'd have to then teach me something that I don't know, and I haven't been able to find in any of the papers I've read about what results are available once the problem has been carefully characterized in that way, right? Give me what you take to be the relevant universality class of the laws of evolution. Give me the right characterization, not of the hawkmoth effect, but of the kind of diachronic hawkmoth effect, and then tell me, is this, are we in the ballpark of this kind of problem or not? And I don't claim to be able to tell you that everything's fine, but I'm not persuaded that things are as catastrophic as they're sometimes led on to be in these papers, based on the results I've seen. Finally, right, this is my last couple slides. Are there then qualitative and diachronic analogs of the hawkmoth effect and structural chaos? I do think there are, right? I do think there do exist things like this. So dynamical systems can sometimes do things like radically alter their attractors in response to tiny changes in the parameters that specify them. Or they can live on what looks like an attractor for a very long time and then pop onto another lobe of the attractor, right? And make it look like the laws that suitably characterize that are the ones that have this attractor, when in fact their attractor is much more complicated. There's a really, I think, great paper for a reasonably lay audience by Ian Stewart called Sources of Uncertainty in Deterministic Dynamics, where he talks about some of these various sources of uncertainty above and beyond just the butterfly effect. And I think it's possible, right? I don't think we should rule out the possibility that the climate system has some of these sort of dynamically pernicious properties, right? I don't think we should rule out the possibility that we're living near a tipping point in the parameter space of some family of dynamical systems, right? And if we did, right, then it might be that we might wake up tomorrow and find that our world has suddenly moved into a regime where none of our models are at all applicable, right? This, of course, would be a catastrophic thing to discover tomorrow, right? And I don't think we want to rule out, this is what some climate scientists sometimes refer to as catastrophic, I have the right word that abrupt climate change is what's sometimes referred to as abrupt climate change, right? And nobody, I think, wants to rule out the possibility that those sorts of things exist. But I think the sort of possibility of those kinds of radically uncertain situations evolving don't seem to me to shift the burden of proof in anything like the kind of way that our authors try to characterize it. Good. So conclusions. My last slide. How am I on time? I can just stop now, or okay. Let me just I'll just leave them up there, and I'll just take questions from now. Thanks.
Thank you. We have 75 minutes for questions.
Sure. Probably we should respond to this. First of all, thanks, Eric. There's a lot of food for thought here. Thanks for engaging with this. So on a philosophical note, let me point out that we shouldn't commit the normative fallacies. From the fact that something really shouldn't be the case, we can't infer that it actually isn't the case. So, and given that, I can reassure you that we actually didn't take the papers to make the case that all non-linear science is completely wrong and nothing can be inferred from it. What we try to point out is that there is something like a spectrum. Here is an extreme case. Here is only non-linear model that I use for very, very precise predictions. Now, you can call what that exactly means. On the other hand, you have sort of very down-to-earth models like an energy balance model. So we have confidence here. We try to argue that at this end of the spectrum, we shouldn't have confidence. There's various paths to get from one end to the other end, and on various of these paths, your confidence in the result probably fizzle out somewhere. We are not committed to any claims of where that is, let alone do we say confidence fizzles out on the entire path. I mean, so you're entirely right to say that we would like to have an answer where this is. And to our mind, this is just an open question. So we sketch the extreme end of a spectrum, and we regard it as an open question where on the way to that end the problem really starts having any bite. So much.
Can I just quickly respond to that? Because I think what I don't understand about that response, the part I don't understand about that response is, so I understand the idea that there might be, right, that there might be a continuum of modeling projects with respect to how much their methodology resembles the core case, right? But this is the kind of distinction I wanted to make between scope and power. I don't understand how that argument by analogy can have moderate power on a kind of class of prediction projects, right? And so insofar as the UK SIP is the same, implies the same sort of methodology, relates to the same kinds of models, right, as basic attribution ones, it seems to me that either falls within the scope of the argument or it doesn't. If it does, it's catastrophic on both. If it doesn't, it leaves both untouched. I guess I don't understand how the argument, I understand how the argument you could be unsure as to how far the analogy goes. I don't understand how you could think that you could say, okay, yeah, this kind of modeling project, and I don't understand why the UK SIP and the attribution ones are different in that respect, and it sort of shows that the argument here has moderate strength, strong enough to kind of obliterate the precise and local predictions, but not strong enough to obliterate the basic causal attribution ones. That's what I find confusing about that response.
Okay, let's come back to the data. I want to say something about the scope of the analogy, which you press on a lot. It can be that the actual example used causes confusion. That's a shame. But with an example, you always run that problem. I mean, the basic point we want to make is that if your model dynamic has model error, then trajectories will diverge. I mean, that's really what matters. Now, nothing depends on there being a probability distribution over it, and there is no reason to believe that if you move away from simple examples like the logistic map, which we took just because you can do it simply on your desktop computer, that the situation would actually get any better. If your model becomes more complex, so why on earth would you believe that they suddenly come together again? And maybe you think there would be an attractor. Well, but then there's no genuine argument for the conclusion that your attractors are stable under structural perturbations. I mean, if you disturb your dynamical law, it may well be that the attractors in the system may be very different, or if you have a driven system, there may be no attractors at all. So the basic point does not depend at all on the use of that particular example, and that's why it is a problem in modeling projects that do not do exactly this sort of thing. I'm sorry if the example was misleading, but I think that the main point stands. And this said, we do mention in the paper that obviously this comes with qualifications. It doesn't happen for all lead times. Maybe an argument can be mounted for models you use in some contexts where lead times are such that you're actually in a short-term regime by the lights of that particular model, and your predictions are right for whatever particular purpose you have. And a lot will depend on what particular class you're looking at. And I think there you highlight a very valid problem. So we haven't said much about functional classes and so on. So that, just like where exactly predictions break off, is an interesting question. I mean, these were the first papers on the topic. So if they raise interesting questions, I think so much the better. So there's certainly more to be said, although in our defense I would point out that section 4 of one of the papers reviews some of the mathematical literature on the subject matter and gives at least some clues about where one could continue with these questions. And I think, I don't know, maybe Lenny wants to add something.
Well, actually we break at 3:30, so we still have 10 minutes. Eric, you want to?
I just want to point out, I just have to point out that there's a kind of peculiar way of characterizing what you think the dialectical situation there is, right? So you give an argument which goes, well, it's an argument by analogy. So it's like I say, well, you know, Hitler was a horrible genocidal maniac, and he was a man. You're a man, therefore you're a horrible genocidal maniac. And then the response is, well, wait. I don't understand why that analogy should go through. And then the response to that is, well, there's no general argument that I'm not a homicidal maniac. So I feel like that's right. So right. I mean, it's again. At the end of the day, right? There's a claim about burden shifting, right? And I don't know when in the argumentative move, the argument that the compelling case was made that the burden is on climate scientists to show that their models don't have the features that this one has, when all you've shown is one very peculiar class of models, one peculiar class of metric between dynamic, et cetera, et cetera. Maybe Lenny has some more.
Sure. So I think the difference between yikes and explosive and catastrophic. So first of all, chaos is not explosive and catastrophic. The definitions of chaos only involve taking limits as t goes to infinity. Like you said, there is some time at which, right? And in a similar way, right, the structural model errors, although they are sort of immediate for probability distributions, they aren't immediate for insight. It doesn't need to happen in any very short period of time. More importantly, your class about the question about function class. So I just looked at Wikipedia. I forgot to last night. So the analogy is pretty broad. It actually doesn't apply to the example we used, but it's for any dynamical system, more dimension 3, and any perturbation which is C1 small, which means you've got a set of equations, and the perturbation you add is continuous with continuous derivative, and you don't multiply it by a big number. That's all min.
But wait, but you need two questions, right? What is the perturbation, and what are the allowable functions I'm allowed to perturb to? If I
hope was,
right,
until Smale, that structural stability was a general property of dynamical systems. What Smale found in the early 60s was that structurally stable systems weren't dense. And then it's not dense in what? And it's not dense if you're in the dynamical system dimension more than 3, which our dynamical systems are, and relative to C1 small functional perturbations, which is just about anything you can think of.
Why does density matter?
So that means that if you actually pick a function at random into space, it is not structurally stable with probability 1. If you put a small
Well, no, right? That's not what I have. That's not what usually. Density just means that between any two you can find another. It doesn't tell you anything about the measure, right?
That's what he was starting to say.
So the word actually used is typical. I think all of these things apply. This is why this was a very disappointing result for an analysis.
Yeah, no.
And it basically meant, and I think it's pretty accepted to me, you have that sort of, the topological differences you get in the way the flows spread. But it's a very wide class. It's not as restrictive as one man, another man.
And you actually don't need to say that in section 4 of the paper.
But let me so the first point, why do we see P09? So we hold that detailed probability forecasts are not quantitatively useful as such. I don't know of anybody else who makes probability density forecasts for 25-kilometer areas for the hottest day of the year for 2083.
But I want to know.
Does anybody else make probability forecasts like that at all?
I want to know why you think the argument. I think this is the key question. I want to know why you think the argument applies to that.
Why in KCP09?
Wait, but does anybody else even in the climate science community do that? There was one project.
I don't disagree. The question was, why do we pick this person? This person did this thing.
Yeah.
Here's what the dialectic looks like to an uninvolved third party. Eric is saying, I don't see in you guys' paper any general argument for explosive catastrophic problems, or even a general argument for yikes. Roman said, well, I don't see a general argument for structural stability and confidence. And I think that the conclusion, I hope you both agree, is there's no general argument either for confidence or...
That's the only conclusion I'm trying to draw. That's the only kind of conclusion I'm trying to draw.
And it seems to me you both have to agree with Eric's point that if we want a sense of what kinds of things we can get out of the models, there's no substitute for looking at the kinds of models that we have and the sorts of things they seem to be reliable or not. And I think we all agree that if we actually look at what, the sort of state of the art, those sorts of things that you're quoting from the UK said 09 look just nuts. We're not going to get that. But there's not a general argument for that. But that comes from experience looking at the sorts of things.
So we're not making the argument that it generalizes everything. I'm just asking, did we choose this target because it was the only target that was out there that was like this?
Well, but I guess what I keep not hearing, and what I want to know
is there anyone else doing this?
What I want to know is what reason is there to think that the argument that you guys have has the cutoff where we want it to
You
fit?
have to let me answer the questions in turn. My turn.
Okay.
Actually, it's my turn, so you can all be quiet for a second. So let's take the bigger question. Are the models that we're using right now, is there any evidence that they're structurally unstable? And I would argue with the decades of experience that we have had, the answer is no, they are not structurally unstable. We play with all of these things all of the time. Every single version of our model is a small perturbation on the previous model we had. They are not structurally unstable. They do not radically give you different results under any reasonable perturbation because you've changed the compiler, because you've changed a small parameter, because you've added in
the
new
compiler argument fails, right?
So no,
compiler say, you mean the GIST model?
No, any model. I mean, and the income model is the same thing. Right? The models.
We have examples of compilers. That isn't structural instability.
It's exactly the same. The compiler makes the code, which makes the calculation, which is the same as changing the parameterization. There's no difference. And there's no evidence across the multi-model ensemble that they are horribly structurally different, even though they are multiple big delta C's with big functional differences within them. There's no evidence of structural instability of the overall solutions in the slides. However, right, so this is a slightly different issue. They are, and they have been shown to be unstable to the inclusion of different physical processes. Right? So I'll give you one example, which is a classic example. The models that predicted ozone depletion that were made in the late 1970s, early 1980s, did not include any physics associated with heterogeneous reactions in the polar vortex. Right? So they all showed that CFCs were going to reduce ozone over the decades to come. They were a big part of why anybody got excited about CFCs and were drivers of the Montreal Protocol. The discovery of the polar ozone hole was completely unanticipated and not predicted by any single model. All of the models were wrong in the same respect because this was new physics, new chemistry that was not included in any previous model. So there is instability of the models with respect to unknown processes that you might not have included, or processes that we know now, but we just haven't managed to include into the models. There is no evidence of structural instability based on small perturbations that would...
if I could just summarize my conclusion in this way, right? I want the conversation to be like that and not arguments by analogy, right? I want to hear about the details of the model. I want to know what...
Mathematical arguments
okay.
about C1 perturbations are not arguments by analogy. The tests that you would do to show structural stability or not are not the kind of tests that we've done. This does not have to be explosive. Chaos is not explosive except in the headline examples. Right? The hawkmoth effect, which comes from a thesis by Erica Thompson.
Well, then, so why do you call it a poison pill, and why do you say that it pulls the rug out from things, et cetera?
So your question
Yeah. This is relevant to your answer to that one question.
So the issue is, we don't know that Navier-Stokes are that we can integrate Navier, they're smooth. There's definitely questions about the smoothness of the integrations of Navier-Stokes equations. This doesn't destroy weather forecasting. This doesn't make our models useless. This doesn't blow up in a short number of days of trying to integrate. But it might fundamentally limit the difference between the solution, the PDEs we think we're integrating, and the numerical solution, and we wouldn't necessarily see that by changing the compiler.
So why do you say they're maladapted to quantitative prediction?
So for quantitative, so first of all, did we get any other targets? I don't think there are any other targets, so that answers the question, why do we pick UKCP?
No. Why do you say that nonlinear models in general are maladapted to quantitative prediction?
Quantitative probabilistic predictions used as such. So if you try to interpret, once you lose this topological similarity, then the PDFs drift away in the same way that chaos destroys making point predictions. Uncertainty in the initial conditions means using RMS error making point predictions are not useful as such, because really you have to make probability forecasts. Right? Probability forecasts in a chaotic system, absolutely nothing need go wrong. So in a structurally imperfect model, the probability forecasts will lose the sort of gold standard that you want. That doesn't mean that they're useless, any more than it means that incorrectly solving Navier-Stokes means that fluid dynamics can't approximate many useful flows. But if you try to say that the probabilities that you get out of the model distributions relate to each other, it can be interpreted as decision-relevant probabilities that you can bet on, then I can actually take money off you knowing only that your model is wrong. And I will succeed with probability 1. And that's sort of a worrying thing. You lose the sort of foundation that we used to have for point forecasting before we worried about chaos. So then the nonlinear, it's nothing about nonlinear models. What really matters is the system. So the same linear models aren't going to save you in some sense. Wow. And the Bayesian method. The point is that this applies to each of the individual PDFs. The idea that you can sort of somehow combine all of these PDFs which are maladaptive or taken as PDFs and get one which is decision relevant in that quantitative way, this is cloud cuckoo land. And there's a paper in the Filtrans by whose first author is the same person who wrote the UKCP09 guidance, which states.
I get confused when the rant starts with, "This is not catastrophic," and then ends with, "You're in cloud cuckoo land." I lose track of what the response is. Yeah.
Right? There's a yikes here. There's certain things we cannot count on. But you said explosive at least 42 times. I stopped counting.
Yeah.
And explosive implies this sort of woof. Chaos doesn't mean woof.
I understand that. Yeah.
On average, it can take as long as it wants before it actually
Well, but then what is the argument that the relevant cutoff, right? What is the argument the relevant cutoff is anywhere in the vicinity of where it would matter to us, that it's anywhere in between UK SIP and attribution models, that, I mean, what, right? Okay, good.
For chaos, knowing only that it's chaos, and even though it's the diachronic crystal, you cannot answer that question. For structural modeling, as soon as the topology diverges, right, then if you, and it's only a question of how accurately you measure things, the distribution is wrong. The PDF does not, the PDF under one system does not reflect the PDF under the other system. Whether or not, if everything falls into your same...
We seem to be back to explosive. I don't
No, explosive, but arbitrarily small. If you only measure there's nothing explosive. What happens immediately is the distributions are clearly the same. But if you only measure to 2 digits, you can't tell the difference. By the time we get to the UKCP09,
How do you know? How do you know? I mean, how do you know that
you have 2 lines
Yeah.
which cross each other. Now they might be right on top of each other, in which case moving on this line gives you exactly the same answer as moving on this line. If they cross, as soon as you move a very little bit, you are a finite distance apart. That's it.
No, but how do you know that the cloud cuckoo land kicks in somewhere between UK SIP and attribution studies?
The question is, if they are very close together, within your measurement accuracy, then you would not be able to tell that the UKCP09 distributions are wider than what you would normally observe in 10 years today. They are really big. And therefore, those PDFs are probably one, will not be expected to reflect the target quantitative probability distribution. Does that make sense?
It makes sense. Well, I'm going to say one last thing. Let's just one very last thing. That all seems very sensible, right? And not at all grist for the mill of claims about the maladaptiveness of nonlinear models for particular, right? Because, right, what you're now saying is, well, look, there's a way of checking whether a particular forecast, given a particular kind of nonlinear model, has taken you into cloud cuckoo land. There's a way of checking, right? If there's a way of checking, right, then the models are not maladaptive to quantitative forecasts because you can then check whether you've crossed that boundary or not. Right? Okay.